from this direction, right? So we could say, well, let's go straight down. That is really the edge of the sphere of where it will be, right? When it hits the ground. Yeah, good, right? So even though it's kind of given to us as like a singular length, we're going to kind of create all spots at that same distance, right? And then create a sphere from that spot. All done. Good. Okay. We should get that. Proper chance. Right? Do you agree with me about where L2 is? Yeah. Somehow like close, like above, they obviously are above the ground somewhere, right? So it should be higher or lower. Wait a second. The person on the ground will be lower? The person who's closer to the explosion will hear a lower volume. Higher, right? Again, make sure that your physics agrees with your real life. You know, this is what physics is all about, is making sense of why things are louder when you're closer to explosions, right? This is it, right? So use that intuition first. Good. So then L2 better be lower. Does it make sense with the equation? Why? Yeah, if the R squared is lower, the intensity is higher. Beautiful. They're inversely proportional, right? Not only that, but R squared, like, that's squared, so it's inversely proportional to the squared. So it's going to kind of have a double effect. Okay, so then we just kind of got to plug in, right? What do we have? Why can't we just jump right away to the 160 meters away? Or what's your method for, did you get an answer here? Yeah, you can, yeah. So you don't actually have to solve for it because you're not ever asked for it, but you can rearrange and plug it in. Or you could do some sort of like, you know, I1 over I2. This is something when you're like, wait, how do I do this without the power, right? And this might happen and this will happen, you know, slightly later. We won't really know the power or be able to calculate or do something calculation about distances away, but we'll know the intensity and we'll know the intensity relative to each other. So what we can do is we can say, okay, that's going to be the same power, but the R is going to kind of correspond to the I, right? So this is, if this is A, but then this is still the same P, right? So let's kind of do that. Let's say this is P over 4 pi r I squared, sorry, or 1 squared, over P over 4 pi r 2 squared, right? And now what? Yeah, you don't even have to cross multiply, right? Because you can, we can do a division. So remember, A over B over C over D is equal to? Yeah, A times D over B times C. Okay, so for us, A was P, D was 4 pi, the bottom one, right? So those two multiplied together, over, and now B was the sort of bottom one on the top fraction, right? Like that's a fraction, that's a fraction, that's a fraction, that's a fraction. So, 4 pi r1 squared, and hopefully you kind of see some things happening here, and then C is also P, right? So what does this mean about our equation? It kind of gets reduced down to a bunch of things here, right? Into 4 pi's, and now it's just the ratio of the two squared radiuses. Remember, all the way back, if we kind of trace all these equal signs back, it's equal to the ratio of the intensities. Okay? So that's a trick to this question. We can plug things in, rearrange for power, but this is a kind of an equation that comes from doing these two things. Whenever you're comparing intensity, whenever you're really comparing, there's a few things. Oh, sorry. There's a few things that will look like this, but whenever you're doing intensity, it's especially one that will look like this. Okay? So that's definitely like an easier method, but we can solve for power here. But in questions where you can't solve for power necessarily, this might be the only method. Okay? And you won't have that case in this one, but you may in others. Okay? So you might be told the ratio of this instead of being told one of them or the other, right? You might be told this one's twice as loud as the other, right? And then, okay, so you're told that, right? So that's kind of a strong inclination to bring up this world too. Okay, so I think we can solve that. Um, let's okay, so this is always something that's interesting to do. Have you ever checked um your thresholds of hearing, how low you can hear or how high you can hear? Okay, so let's do it. It takes like 2 minutes and it's like interesting to see how high you can go. Some people like are really low. So do you have headphones? Or am I on am I on like just the speakers? Yeah, I think it'd be helpful to have headphones. Don't have it too loud, okay? But what we're going to do is we're going to generate frequencies, right? And what are frequencies? What do I mean by generate different frequencies of sound? How will the sounds differ? Sorry, the first time I phrased that question was terrible, but how will the sounds differ? The pitch, which is like high low, right? Is it inverse? Is it like high pitch is low frequency or low frequency is high pitch or vice versa? Is it like low pitch and low frequency? Yes, good. Okay, good. So it sounds like you already have that connection of High pitch, high frequency, right? Like people say that sometimes, like, oh, it releases this really high frequency noise. Like you can sort of interchange it with pitch, right? Good. Okay, so let's start with really low. So we're going to talk about kind of frequencies here. We're going to use the unit of frequency. So before I kind of give this to you, we're going to talk about frequency of sound. Frequency, kind of like when I ask you how frequently do you go to school? Give me an answer for that. Almost every day. Okay, so give it to me then in sort of like the unit that gives me the best representation. If you need to give me it a fraction possibly out of 7. 5 out of 7, right? 5 out of 7 days. Okay, is the days on the top or is the days on the bottom? Or is it on both actually? It's on both. It's on both. Okay. Let's now rephrase this to 5 visits. How many visits to school do you have per week? Right? So I kind of phrased it as how many days per week do you, and now your answer was 5 days per week, right? I go to school versus 7 days out of the week, right? Well, here you're going to say 5 visits per day, right? Well, what if this was like how many times do you take a insulin shot per day, right? What might be an answer to that? How many? I mean, I don't necessarily know the true answer. Like, I guess it kind of depends on your diet. I guess you take it. Let's say you take it like once after a meal if you need it. Okay. So how many times might you take an insulin shot per day? Ooh, okay, okay, good. So you were thorough in your answer. Okay. I asked per day, right? So you could have gotten away with saying 3 times, right? But implicit in the answer was my kind of per day. It's good. It's great that you said per day, okay? But 3 times per day, this is a number of events, which doesn't really have a unit, but you'll notice that the bottom kind of always has to be time, right? So it's events in a certain amount of time. That's how we say frequency. How frequently did it happen? Well, we're talking about in a certain amount of time, how much did it happen? That's one way to measure frequency, right? And then another is um, how much time did it take you to get to 100 occurrences, right? Like that's another way to measure frequency, right? So what we're doing there is we're either fixing the number of events, 100 events, and saying what's the time, and now I can calculate frequency, or I could fix the time and say in 1 day, right? I could fix that, and then I could ask how many times does this occur. Now I can calculate frequency, right? So you and I in our language are pretty loose in sort of talking about, events and time and all this. But frequency, its true unit, is number of events per time. So its unit is 1/seconds, which is like we're starting to get into the world of units that kind of start to make less sense, right? Like meters, seconds, joules, those all kind of make a little bit more sense. This frequency of sound is measured in per seconds. Okay? So that unit, you've seen this before, is what? What is Hz? Hertz. Okay, so Hertz was a scientist named after Hertz, and it's 1/seconds. Okay, that's the frequency of sound. Well, what that is what event are we talking about? What's the event that we're talking about? What's a sound event? Or if it's another thing we could sort of yes, exactly. Nice. Waves, right? We could have said cycles, maybe would have been a bit more representative word, right? Number of sound cycles, right? Because how many times does it cycle per second is the frequency of the sound. Okay? Number of wave sounds per second. So in in 1 second, how many times will I see that sound wave jiggle up and down? Okay? Okay, so all that is to say that we're going to go to a frequency chooser here, an online tone generator. Okay. So I can't vouch for what volume this is at the start, so just kind of have it, set at the start and then slowly just increase it until you hear it. And first just I think it's set at like 440 when you first get there. So, yeah. Okay. So I'm going to kind of like put the volume down a little bit and I'm going to play it and I'm going to see kind of if I can hear it. Okay, I can hear like a small sound. I'm slowly increasing the volume. Yeah, at about half, it's not so loud for me. Yeah? Can you hear it at 440? Okay. So so hits like if you want to keep it going, but I stopped it. It's kind of annoying. So we're gonna get to those sounds that are kind of like brain itchy, right? You know what I mean? They're like like the really like they hurt, they almost like scratch in some way, right? And we're gonna get all the way down to the like guttural, like really really low sounds to the point where you start to lose it, that it's not even creating sound anymore. Okay? So which one do you want to do first? Up or down? Okay. So up is harder because the range is quite high. Okay, so put in a number and see if you can hear it. Tell me what you put in. 500. Okay, go for it. See how much it changes. Yeah. Okay, so go crazy. Can you still hear it? Yeah, but it's quite high pitched now, right? Okay, so 5,000. Let me hear that one. Oh yeah. Oh, yeah. Okay, so keep going. You can't hear it anymore. No, 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 no. You have to. It has to be your headphones in. Yeah. What volume do you have it on? Like, where is the meter relative to your? Oh, sorry. Like on the screen, you also have a volume meter, right? Okay. Mine's like right at the stop. Mine's right below stop. Okay. But it's like I can go like relatively high. No, we're not going to damage anything unless you're like legit, like you have your headphones blaring and you have it on for like 3 minutes. Okay. So is it 80,000? Okay, it's got to be the headphones then that like don't do that frequency. So maybe even go higher. See if it can do a higher frequency. It might be the headphones. You can hear it now? No? Oh no. Oh, you got robbed. I'm sorry. Okay. So so let me see. I'm gonna see where mine is. So I'm an old guy now, so your hearing slowly goes down. Have you ever heard about those ringtones that only young people can hear? Yeah. Okay. And it's like obvious because everyone goes like ah, right? Like it like hurts everyone else, right? Well, young people, young ears can hear like I think the limit is like usually about 22,000. Okay, no, 22,000 is kind of crazy. So the highest I can go is 20,000. I can't hear it. Okay, so I'm gonna go down. I'm gonna go to like 16,000. Or no, it accidentally put in 12, so I'm gonna see that. Yeah, I can still hear 12,000. It hurts, but it's still there. I can still hear 15,000. I can still hear 16. Like, but I think honestly the headphones um do play a part. So you might even be able to do this on your speaker, right? See if your speaker can do it. Take your headphones out. Oh yeah, I hear it. No? Okay. Okay, sorry. This I don't know if this one is maybe not so great, but there are some others on the internet, so it might be worth it to even try because there are some that you can get up to like 20,000 or 30,000, right? Okay, so let's see if this oh yeah, this one I think is maybe a little bit better. Let's try this one here. So let's go down all the way as far as we can go. Okay? On this one here. Sorry. Oh. Oh. Yeah. Just make sure your volume's a little bit low. It does like scrap. This one actually gives the musical note too, which is interesting. Yeah. Okay. So, yeah, this one's a little bit louder, eh? Yeah. You can? Wow, that's awesome. Okay. So I can't quite hear that high. Let me see what I can hear at here. Oh no. Last time I did this, I could hear around about almost 17, but now I'm like midway between the 15s. I'm losing it. Okay, but I mean you don't have to hear those frequencies anymore, eh? But okay, so let's go all the way down to the low side then. Are you down there already? Where do you lose it? 35? You can turn this one up a little bit because it's a low sound, so it won't hurt so much. Yeah, you can feel it. It's almost like you can feel it, right? It's weird how that sound affects you that way. But okay, so that what that means is that is just a speaker jiggling 27 times per second, right? To say like 27 hertz. That's like almost as fast like you could almost create a speaker with your hand motion that fast, right? Like that's pretty fast, 27 per second, but like, people can like press buttons at like 16 per second, which is like pretty good, right? So like you could create a little speaker just yourself just by moving so fast, right? So we can hear quite a range, okay? Um, things like bats, and like this is, something that's like interesting to look at the different ranges and different animals. Um, and honestly, like I think for a lot of like mammals, the response, the way we test this is that like cringe, like you're hurting my brain response in animals as well. So, um, okay, so let's just look back here at, so that's kind of like, our threshold of hearing. Our threshold of hearing in terms of volume is uh 10 to the negative 12 watts per meter squared. Okay. So this is something that Alexander Graham Bell defined as 0 Bell. Okay. And so we can find the sound intensity as a relative value compared to our ability to hear the tiniest, littlest thing. Okay? So the limit of hearing is 10 to the negative 12 watts per meter squared. What was this sound that we never actually figured out, but like this one here was our intensity there, right? So that's 0.2. That's 10 to the negative 12. So this is a billion times louder than something we can hear, right? So the reason that, you know, or like, because these things are so huge in range, zero point 0.2 was the example we just looked at of a sound. It was an explosion, but we might look at the sound of, huge things, not just necessarily human hearing, but something that, is the sound of some collision or something, or a jet or something. But regardless, like look at the range. This is a billion times bigger, okay? So this calls for a logarithmic scale, just like the pH, right? The pH is like the acidity stuff from chemistry, and it suffers from the same problem. All the people in their relative, ranges, they're in billions and billions of each other, right? Billions of times more acidic. So that called for a log scale as well. Okay? So what we're going to do is we're going to take the log of whatever intensity you're talking about, and we're going to use this I naught, which is the threshold of human hearing. And we're going to divide it by that value, and then we're going to take the log of it. So this, in this example, our I value of the sound we were talking about was 0.2. So we would take 0.2 as our I value. This value is a constant. It's how low humans can hear. That's not something that's going to depend on the question you're doing. Right? So then you divide these two, and then you take the log of it, and that is how many bells. But you probably haven't heard this scale before in bells. You've maybe heard it in another unit, a multiple of bells, tens of bells, decibel. Have you heard of a decibel? Yeah, that's what that is, right? So this is going to be bells, and then decibels is going to be just us kind of like dealing with the fact that these numbers always come out in hundreds and thousands and stuff. Okay. Um, okay. So, um, okay. So let's get a value here, 0.2 divided by 10 to the negative 12. And we get 2 times 10 to the 11. And now we have to take the log of that. We get 11.3. Okay. So that is the that is the scale that we'll use. Okay. So there's just a 10 out front. Okay. Basically, there's a 10 out front. So that's the number of decibels. So there's a 10 out front. So this is actually 113 decibels. Okay. So decibels, which is a 0.1 of a bell. Okay. Okay. So this is kind of like our comparison of normal sounds to in their intensity and their intensity level in terms of decibels. Okay. So what's nice is our threshold of hearing is 0, and we'll always kind of like talk about things. Well, I mean, we don't necessarily always have to talk about things. If you get a negative decibels, it means we can't hear it, right? Okay. So, sorry. Okay, so that's our sort of like sound intensity section there. I just want to take a look here. Oh, okay. So there's a little bit of a section that talks about echoes. Do you know what echoes are? You know, like there's a whole slide on what an echo is, right? It's a reflection of a sound wave. Yeah? Comfortable with that? So sound is restricted to a formula. Okay? So the formula for the speed of sound. Okay? So uh, because we now will be able to sort of like use frequency. Remember that we can use this frequency and the wavelength to talk about the speed of a wave, right? So if we know the frequency based on the pitch of the sound and we know the sound, then we can figure out the wavelength and we know everything we need to know about the thing, right? So the way the speed of sound in a normal sort of room temperature is, well, how about let's say at 0 degrees Celsius, okay? At 0 degrees Celsius, it's 331 meters per second. And every 1 degree Celsius that goes up, we go up by 0.6 meters per second. Okay? So that's a language way to say start at 331 and add that to 0.6 times your temperature, or the temperature in Celsius. Okay, so this is for temperature or for sound in air. Okay. Okay, so let's kind of like just practice this, but what this means is we're going to do speed of sound and wavelength and distances and echoes and frequencies. We're going to be able to sort of like, I'm going to be able to say, I release a 20 or 200 hertz sound here, and it takes 3 seconds to get back. how far away am I from this? If the temperature is 3 degrees Celsius. So let's try it. Let's maybe make this a little bit better problem here. So I hear an echo from a wall after 3 seconds at 3 degrees Celsius from a 200 hertz sound I made. How far away is the ball? Let's do it. Okay. So what would you do? Do you have an idea what you're gonna do? Because the sound is traveling how far? Yes. Okay, so delta t is 3 seconds, right? Remember that it's traveling there and back. The frequency that was released was 200 hertz, right? The temperature outside was 3 degrees Celsius. Why would they be telling us the temperature outside? Well, with this formula we just learned, right? The velocity of sound is 331 plus 0.6 times the temperature in Celsius. So we can find the speed of sound. Would the speed of sound help you here? With the speed of anything? If this was a car going back and forth and you knew that it took 3 seconds, if I told you the speed of the car, would that help you figure out how far away it went and came back? Yeah. We can just treat sound like it's a thing that's going back and forth. So if we can find the sound speed, so let's do it. So 331 plus 0.6. Oh, got the 3 in my head. 0.6 times 3. So we get what? 332.8. Okay, and that's meters per second. All right. And so that's the velocity of the sound. Well, what did the time, how long was it traveling for? Okay, and what do we get? 998.4. And unit? Ooh, what are we finding? Meters, how far away, right? Just meters. Okay, I have a question. If I told you that I had a car and um it took 3 hours to go there and back, okay? And I was traveling at 332.8 kilometers per hour, and I asked you how far it was from A to B, us as Canadians, we oftentimes we say, if I ask you how far away is something, you'll tell me, oh, it's 3 hours away. I asked you how far it was, and you told me a time, right? Would you say that this destination is 3 hours away? Why? Well, yes, no, but that would be like, okay, so okay, can you like tell me something that's like 3 hours away from you? Like a city? Like about 3 hours away from you. Okay. So you go to Rochester and you come back. How long does it take you? 6 hours. So if somebody asks you, "Hey, how far away were you?" You won't tell them, "Oh, I went on a trip 6 hours away," right? What's the problem here? Yes. An echo travels to the wall and back. So this delta D that we found is how far the sound traveled, but the sound traveled twice the distance that we're looking for. Okay? So this is the trick question of this section, and it's really kind of the only question that is ever challenging. Like the other questions are really just this. It's this temperature outside. How fast did this travel? Like, okay, sure. Right? What if I asked you what the wavelength of the wave was? How do we find the wavelength? Yes, good. So if we know the velocity and we know the frequency, then we should be able to find lambda. Okay. Okay. So it's what, like 330, so it's like one and a half-ish? Oh, 1 point, whatever, 0.1-ish. Okay. So, I think that's kind of everything. I'm just taking a look at the other questions here. Uh, So, right, and okay, so let's talk about echolocation, right? And really, ultrasounds do this too, right? So, and this is really like a very, very common method of detection throughout our world, right? We see it in mammals, we see it in bats, we see it in dolphins. What are they doing? Echolocation. What does that mean? Echolocation. Yeah. Okay, let's say that you lived in a little canyon, okay? And in fact, you no, let's say that you become an echo expert, okay? You spend your days going to canyons and standing at one end of the canyon, or going to rooms and standing at one end of the room and listening to how far away the echo kind of comes back. So as soon as you walk into a room, you can kind of tell like, "Oh, this one is bigger than that one I was just in because the echo took longer to come back." Right? Well, pretty soon, I mean, that's basically you already have a method of being able to sort of tell how far away the wall is, right? And in fact, and our human ears are capable of this if we train them. And I think your teacher's going to show you a video, it looks like, that I've seen. It's actually pretty interesting. It's cool. But um, bats and dolphins, they have this, this is their really common method for quote unquote seeing. And it's the same method that we use for ultrasounds and things like that, which is that I'm going to send out a wave, and if I detect, so let's say, for example, the shape of the thing looks like this. Okay, so let's say it's it's a bull in front of me, right? I'm going to sort of detect that reflection first, and then I'm going to kind of like, detect some other reflections, right? A little bit later. Yeah. And I'll slowly, like this is I chose a terrible shape here, but basically, like, let's sort of choose one that has a shape that all points directly towards me. I'll be able to tell that the certain thing is closer to me versus this thing over here, which is sending its reflection back a second later. Are you with me on that? So I can now sort of detect the difference between two different objects, right? If I'm precise enough. So the method is precisely that. Okay, so animals have gotten to this level where they can kind of detect, like, no, first of all, normally they wouldn't hear an echo if it was just continuing on. So as soon as they hear an echo, they know something's in front of them, right? So there's that, right? But then there's always like small echoes. There's a small bit of something that's kind of like there's a little thing over there. There's whatever, right? There's a chair. It might look like a something, whatever. The um the echolocation. So I mean, if you want to, we can watch this video. I think the link is here. Yeah, it's there. It's pretty interesting. I think it's a boy that went blind that started to like use a consistent click. So the sound, in order for your ear to develop the difference between different things and to be able to detect it, you have to be able to create a very consistent sound. So he learned to create this very consistent sound to be able to hear things around him. Uh, and he can, to the point where, like, there's a scene I think in this news thing where he's having a pillow fight and he detects where the person is and throws a pillow at them. And like they're walking down the street and he can like, oh, there's a garbage can right here. There's like stuff in his way and he can walk around it. I mean, it kind of looks like there's one scene where they like it looks like they put something in front of him on the sidewalk and he walks around it, but it's just like, okay, well, are we putting stuff in front of this guy? But it's pretty remarkable. So the method is the exact same. Okay, create a sound based on the reflection of the sound. You're going to detect something. And so, have you ever heard about those like fish detectors that you put in a boat, and like under the boat, it can sort of tell where the fish are. Have you seen one of those before? Okay, so they have those. It uses echolocation, okay? It's also the same way that boats, like all just like big freights and everything, how they detect the bottom. They send a message down to the bottom of the, and you'll probably see a problem like this, honestly, because I can now add a little velocity to this thing and make this thing an interesting problem, that the sound wave kind of has to travel a little bit different distance. It doesn't have to travel just straight up and straight down. It has to travel a slightly different distance. So this is sometimes a way that we can kind of trick you, but regardless that the thing is programmed, it just creates a sound, and then when it hits the ground, it reflects back up, and I can detect that. And now, based on how far that reflection is, right? Oh, the reflection got a little slower, right? It's taking more time to come back. Okay, so that means that we're now at deeper water, right? Because it's a little further away, right? So that's how it can sort of detect that. And ultrasounds are the sort of same way, okay? Ultrasounds create a hypersonic, hyposonic, hypersonic. Sonic means hearable. So hyper means sonic, means a frequency above hearing range, hypersonic. And hyposonic is below hearing range. Okay? So it creates a hypersonic sound that um, it's very, very precisely detecting the difference in reflections to the point where it can detect the difference between like the membrane on something and an actual like organ, right? So those things are very, very precise. But there is a difference, right? Like if you're super, super precise, and that's why, have you ever had to have an ultrasound of anything? So they put that like jelly, right? The jelly is so that there's no air, because if there was air here, then the way that the sound travels through the air, the time that it would take to travel through the air is different, and it will fool the instrument into thinking like, oh, there's a bunch of dense thing here or something like that, right? So or it will think that there's nothing there when really there is. So the jelly is about the same, kind of consistency um, as our bodies, that it takes the instrument can deal with the fact that it's traveling through jelly. Okay. So okay. So let's all right. I think that's it. Let's just see. Okay. I mean, oh, Mach. So traveling Mach 1 or Mach 2 or Mach 3, okay? Have you heard this before? Okay. So Mach means, and like, yeah, it's kind of been like co-opted by like advertising, right? Of for some reason it makes me think of razors. I'm sure there's a Mach something razor. But a Mach, M-A-C-H, one Mach is traveling, or this is a speed traveling at one Mach, or Mach speed, right? I'm sure you've heard that, is the speed of sound. So what happens when we go faster than the speed of sound? Yes, good, right? So have you seen that like happen in real life? Are you like referencing something where you've sort of like maybe like see somebody like swing a golf club or something far away? I don't know. That's the one that I can think of. Lightning. Oh, yes, for sure, for sure. That's probably a more relatable example. Okay. So, um, so yeah, okay, so that's light traveling faster than the speed of sound, right? But have you ever heard of, like pilots or something, or like airplanes going Mach speed or faster? And what happens? They have to break a barrier to do it. Have you ever heard of that? Breaking the sound barrier. Have you heard that before? What does that mean? Do you know? Okay, so let's see. Uh, I think there's a pretty cool YouTube video of. So what happens? So this is okay. This is a 10-minute video. I don't know this, but let's see if I can just get the. Oh wow, okay. Um, okay, so some nice YouTube montage, dance music on the back of this top five, but just okay, just skip to like 58 seconds, and let's just watch this kind of plane go through the air here. It's like just going faster than the speed of sound. Oh, sorry. Okay, sorry. So the did you see the second one too? The second one actually gives a really good like interpretation of what it really looks like in real time. So pretty short too. Yeah, it's pretty interesting, right? So what's happening there? Because sound, remember, what are these waves made up of? What are they made up of? Sound waves. Those all sound waves are a little compressed area of uh air particles, a little compressed area of air particles, and then a little bit of a decompressed and not so many particles, and then a deeply compressed area of particles. Okay? And then a not so deep area. And the way we sort of like feel this is like a vroom, 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 like a, you can kind of like picture it, the deep bass of a concert. You've sort of seen that, like thing in videos where you can sort of see the air coming, you know, and moving in like a compression decompression kind of motion, right? So if you're one air particle in this journey, maybe you'll kind of like just kind of wiggle back and forth, but the sound as it travels this way will squeeze things together, and then horizontally that will be next to a decompression, and then a compression, and then a decompression, and then a compression, and then a decompression. And that's how we're going to kind of mark the wave of the up down of this wave. Okay? So so sound is what's called a longitudinal wave. You heard that before? Longitudinal? What does that mean? Longitudinal. Well, most things like water waves are not longitudinal. They're transverse, right? Because if you're one particle in this water, you travel up and down while the wave travels to the right, right? But if you're a sound particle or you're a particle of sound, it's not a particle of sound, particle of air, and there's sound passing through you, you're gonna just travel shift left and right, and the wave is also traveling in that direction. So this is longitudinal, where the particles in the medium shift in the same direction, and this is transverse. This is like most waves or most things that we identify as kind of like having a wave shape, we identify as transverse waves. Okay? Okay, so sound is a longitudinal wave. Okay? And so, but the wavelength, it will kind of still be a hump and then a valley, and then a hump and then a valley, right? We can kind of still represent it. So it'll just be from peak to peak. That's still a full wave. Okay? Okay, so what's happening with breaking the sound barrier? We have sound waves here, and basically the sound of this thing, it's pushing in. So have you talked about the Doppler effect? Okay, maybe you and I have talked about it, right? Like, what is the Doppler effect? Yes. Yes, good, right? Like, like that sound is synonymous with me with the Doppler effect, right? So you're as you're moving to the right, you're kind of creating more space. Like if you're kind of creating compressions, decompressions, your decompressions will be further kind of apart, right? And your compressions will be further apart. Well, what that means is the wavelength of the sound that you're creating is greater, which means its frequency has to change because its speed isn't. Speed of sound doesn't really change. But as you're moving forward, you're kind of moving into the things that you're creating. So they're actually going to be compressed down together. Okay? So the Doppler kind of says that you're going to compress the ones in front of you. Well, breaking the sound barrier is going so fast that you can't really go fast enough for the waves to still be created in a forward direction. The waves are not going to be created in a forward direction. You're going to create your waves in a backwards direction. Okay? So you're kind of going faster than the wave can go to create. You're going faster than the speed of sound. That's what it is, right? So it's like the moment of traveling faster. So what there is there's a buildup, a buildup, a buildup, and all the waves are getting built up on top of each other for a split second, and then you burst past that, and that's your breaking the sound barrier. Okay? So they're all built up at the same spot. Okay. Okay, cool. I think honestly that's like about it for this section. Um, just trying to take a peek if there's anything else. Oh, so I would say we've kind of tried it, but your practice problems now, the supplementary problems on decibels, that's a good practice now. Okay? So try to play around with that and your formulas there. We could try this to here. I don't know. How are you feeling? Yeah? Okay. Let's do it. Um, oh, shoot. Okay, sorry. What is the what is the temperature outside? Or what is the temperature? The air. What's that? Sorry? Yeah, exactly. So we have two different mediums that the sound is traveling through, right? Right? We have the ocean for most of the journey, but then for the last little bit, there's the 300 meters of air. Yes, good. The 300 meters and the what? And the so it took that long to travel 300 meters? It didn't travel 300 meters. They didn't detonate it at the surface. Where was it detonated? Yeah. So I don't know who these people are setting bombs off in the bottom of the sea here, but the point is that the sound has to travel up first through the sea, through that 3,000 meters. So first, that's going to take some time, and then from the remaining time, we have to travel that 300 meters, right? Wait a second. That makes sense. So what's our time that it's going to travel here? Well, we have D. To find time, we'll just need V. And we have it. So just in the sea, we should be able to say how long that takes. Wait a second. Sound travels through water at 1500, right? They tell us that speed there. So then they tell us that speed in the water and the distance in the water. We should be able to say the time in the water, and then we'll take that. Yeah, 2 seconds. So now we'll use the 300 meters and just the 0.89 and figure out velocity and then that will get us to temperature. What's that? Well, that's the time that was in the sea, right? No, no, no. The pilot hears the blast after it was detonated, right? So that is the time it was detonated, 2.89 seconds after. Well, if it took 2 seconds to get through the sea, why did the pilot hear it 2.89 seconds after? Because it still had to travel through the air. So how much time is remaining? Yeah, that's the time in the air. And what is the distance in the air? It's that 300 meters. And so we should be able to say the velocity in the air based on that. Okay, so when do we get there? What is it? Sorry? Okay, and that's meters per second. And so what does that have to do with the temperature? Yeah, that equation that says that for every 0.6 degrees Celsius above 0 degrees Celsius, you will, sorry, for every degree Celsius, you'll gain 0.6 meters per second, right? So now we just plug it in and we can solve for the T. So I get 10.17 degrees Celsius, which makes, yeah, seems to make about sense. It's a little bit warmer than air. It's going a little bit faster than normal, or than 0 degrees Celsius. Okay. So yeah, this is a way that we can kind of like add in this thing here, but really this is just a velocity distance time kind of question, and you just have to sort of make sure that you're only using sound traveling in air when you're using this equation here, right? Or when you're using this equation. Okay. So, um, yeah, I think we're pretty much, that's like all of the question types that you have. Uh, yeah. Um, so I just am double checking here. Yeah, okay. So, yeah, I mean, we're kind of through here, but really it's now just about kind of like doing questions. Like, honestly, this section isn't as scary once you sort of like just see everything, once you get to know it. Like, even that, I'm sure you're not too intimidated by that equation, right? Like, there's only one unknown in there, so that's nice. Right? Okay. So I'll send you our PDF, and do you have an idea of when you